Welcome to the PH4410 review of random matrix theory. Earlier on, we have seen how the theoretical Pastor-Marchenko distribution looks like, and also did an octave exercise on plotting the eigenvalue distribution of an artificial correlation matrix formed by first creating an artificial random time series cross section. Now let us look at what the random matrix theory will tell us if we actually use a real time series cross section. In this particular example, I will use the data from the Singapore Stock Exchange SGX. I had a previous student that had done some work on it, so he passed me some data. So I'll just load the data itself. Okay, and these are all the variables, so don't worry about most of them. We are only interested in the prices variable, which is over here. So you can see, most importantly, that there are 947 stocks and actually over 8,096 time points. So the Q, for this case, Q equals to 8096 divided by 947 is about 8.5. Okay, so now let me first compute the correlation matrix over prices, and then check that it is 947 by 947. Now I've done this example before, so I know that there is some problem with this correlation matrix. There are some matrix elements that are not a number. So let me first find what these are. Find using this particular function here. Find isNan C, and it will tell me that row number 499 will give problems. So let me remove row number 499. So this can be done by going from 1 to 498 and then 500 to the end for the rows, and the same for the columns. 500 to the n. Okay, and let's do the find n again. You see that there's no more problem. So, but now of course C is deflated by 1. So my Q should be equals to not divided by 947 but by 946. So it's increased by a little bit, 8.56. Okay, and now we're ready to compute the eigenvalues. L equals to EIG of C. Okay, and in fact you can plot you can see how the matrix look like. It's a lot more interesting than the artificial time series, so you can see a lot more red, indicating high correlations, and lesser blue indicating negative correlations. So we're not that interested in this particular color map. So let's go and compute the theoretical maximum eigenvalue, which is 1 plus 1 over q plus 2 over square root q, and that is 1.8. And at the same time, to compute the minimum one, 1 plus 1 over q minus 2 over square root q, which is 0.43319. Okay, so let's now first let's create the histogram for the eigenvalue for the SGX correlation matrix. So n bin L bin is equals to hist L. Now in the early exercise we saw that actually 100 bins is a little too many, so let us try say 50 bins and see what it looks like. Oh, so first of all, for real correlation matrices, sometimes you end up with negative eigenvalues because this is a rather big matrix. So let's just take the real part of the eigenvalues and do this again. So now we have it, and let's do a bar graph to see what it looks like, L bin, N bin. So to see whether 50 bins is a good number. So it's not that good because there are very large eigenvalues in this problem. So we need to go to say 500 bins. Let's do this again. Okay, so obviously the large eigenvalue is not what we're interested in. L max is only 1.08, so let's check and see what it is like if I go from 0 to only about 2 or maybe 5, and then 0 to 100. Okay, so actually there's not enough bins here. So 500 is not enough. So let's increase the number of bins to 5,000. Okay, and bar it again, bar graph, create the bar graph again, and take a look at, now this is much more interesting. Okay, but there's still a lot of zero eigenvalues. So let's increase the number of bins yet to 10,000. Okay, create the bar graph and then see what it looks like. Is it more interesting? Yes, there's a lot more features that can be seen between 0 and 2. So now let's go ahead and compute the maximum eigenvalue, or we've done that already. So let's plot the theoretical distribution between L min and L max. 500 data points should be enough. And then PLL would be equals to Q divided by 2 pi, okay, times the square root of L max minus LL dot star LL minus L min, and then dot divide by LL. Okay, so and also I need to normalize N bin by dividing it by 400, and also DL bin, which I have not calculated yet. So DL bin is equals to diff of L bin 1. Okay, so now N bin, let's normalize it as N bin divided by 400 divided by DL bin. Okay, so now let's do the bar graph again. Okay, and set the axis to be this, but now it is no longer up to 100, but maybe about 1. Yes, 1 is fine. Okay, so let us now plot the theoretical distribution. Hold the plot and plot LL, PLL, red, and then with a line width of 2, and see what it looks like. So actually you can see that the, okay, let me increase this a little bit. You can see that the empirical distribution, the empirical eigenvalue distribution of the Singapore Stock Exchange doesn't look anything like the Pastor-Marchenko distribution, and that may be because we have too many very small eigenvalues. These kind of eigenvalues may be because there is actually the data points, the time samples are not fully uncorrelated, and if they are negatively correlated, we end up with this kind of situation. So you can see that in the real data there can be eigenvalues that are a lot larger than the maximum theoretical eigenvalue, as well as eigenvalues that are a lot smaller. In fact, the largest of the empirical eigenvalue is 503. This corresponds to something called the market mode. So the eigenvector associated with this eigenvalue is called the market mode, and we will investigate that in the next video.